In this lecture, we're going to add another particle model, namely the one inside a potential well. So that's going to extend upon the previous model, so it didn't have any potentials involved. And it's going to lead us on to something called the harmonic oscillator. So you will recognize this if you have done the physical spectroscopy course, because that is the founding principle of vibrational spectroscopy, and we can model diatomic molecules with a simple harmonic oscillator model. And we're going to do a little bit of maths to help justify it, nothing too strenuous. We're going to make a couple of simplifications to make it a little bit more approachable, but it will show why the harmonic oscillator is quantized, where 0-point energy comes from, and so on. So to briefly recap the previous models, all of the models that we've looked at so far have had no potential, or at least no potential that can influence the particle. We can drop a particle into the box and it can move around however it wants within the constraints of that box. So there is no potential, therefore there is no potential energy operator. So remember, the potential energy operator, V with the hat on, simply equals the potential itself, a function. And if that is 0, well, we may as well ignore the potential energy operator, it's all 0. That simplifies the Schrödinger equation down to this. You can say that's simple if you like. It's simply a derivative and a couple of constants, fairly straightforward. So let's add potential energy back into this. What is potential energy? If we recap it briefly, potential energy is about an arrangement of a system. If we talk about gravitational potential energy, we could raise something up and then that would gain potential energy because its arrangement with respect to the Earth has changed. Or if we're drawing a bowstring back, we're changing the shape of the bow, we're changing its arrangement and its configuration. Its potential energy will change. And a potential, at least the way we're talking about it now, is how that potential energy changes with respect to the arrangement, or with respect to space, with respect to some kind of coordinate. So imagine we did have this relaxed bowstring. It's at the minimum point here. So X is where we have it relaxed. As we draw it back, X increases, that displacement, the potential energy goes up. So a potential is sort of a graph of how potential energy changes with respect to distance or coordinate. So it must be some kind of function of X, and we just call it V of X instead of F, just to say that it is a potential function. So that's the notation we're going to use. So these systems must all include potential energy operators, and that complicates things a little bit. So we have here our kinetic energy component, T with the hat on, and here we have V with the hat on. So there is a complex potential function there. Could be any kind of function. We're going to pick one in a moment, but we're multiplying the wave function by it. That changes a lot of things. It means we can't use the same wave functions that we were using previously. So let's describe the harmonic oscillator for a moment, or the harmonic potential. Here we simply have a parabolic graph that just goes down and then up. There is a minimum, and this curve is sort of related to x squared. And if we're talking about the harmonic oscillator, well, it's half kx, where k is a force constant. It describes the strength of the field, and a half, well, that's there to mostly keep the numbers matching up when we take derivatives of this to work out force. So the half becomes quite useful for us, but it is sort of an arbitrary choice. So we can rebuild the Schrödinger equation like so. We have kinetic energy here, one dimension. There is a second derivative with respect to x, and we also have the potential energy operator here, which is just half kx. That is the function that describes the potential. But what is the wave function? I've highlighted that in orange. What is it? Well, we could try the original sine, for instance. Let's stick that in. And what happens when we derive sine? We get this, and suddenly when we try to extract that function again, we've got a wayward x squared here. That's a variable. That is not a constant number, so it is not an eigenvalue. So therefore sine x is not an eigenfunction. We can't. Once we add a potential energy operator in, that beautiful bit of simplicity of just using a sine wave ends, unfortunately. And this should make some sense, because if a sine wave just continued along almost indefinitely, we can see that the probability of finding a particle is actually fairly well distributed. We could find it here, we could find it here, we can find it anywhere. In which case, what would the potential be doing to the system? This potential here is high here. It must be forcing the particle in this direction. It's high here. It must be forcing the particle in that direction. The particle should be more likely to be found closest to where the potential is lowest. That's what a potential is doing. So ideally, our wave function should look a little bit more like this. It should be bigger in the middle and then decay off to nothing. So as the potential increases, it requires more and more energy to push a particle there. Therefore, it should be less probable that we can find it there, so the wave function must get smaller. And yes, strictly speaking, it is the square of that function that determines probability, but you can also see it in the wave function that it is larger here. The square of it's going to be larger there as well. So I'm not going to bother deriving why this is the case. We're going to do it by a simpler method next term, but this is the wave function, and it does look like a very complicated mess. It's difficult to wrap your head around this wave function at first sight, but we are going to simplify it. We're going to hide some stuff away and sort of forget about it, just to make sure that we know how the underlying maths and physics works, rather than focusing on all the details. So let's split it up into three components first. So I have an additional video on how to chunk up equations that basically show you this. Now those are just numbers there, and those are constant. Here in the middle in green, this is some kind of function, and it is a polynomial function known as the Harmonic polynomials. It's given down here. Generally just look up the results rather than trying to calculate it. And then finally we have this exponential function here. So the exponential function effectively just looks like just an exponential curve. It simply drops away. It's biggest in the middle and then drops away to nothing eventually. That's a lot closer to what we expect from the previous diagram. We want it to be, the wave function to be really small as you get further away from the center. So let's begin to simplify this away a bit. Here I'm just going to crunch these things down into just numbers. We don't really care what that is right now. It's just a number that scales the wave function up and down so that total probability becomes 1. Here we just know that this Harmonic polynomial is a function. There are various ones depending on which energy level you want to check. We're only going to focus on where it's equal to 1 anyway, and here's a simplified version of that exponential. So if you plot that into a graphical calculator, Excel, Wolfram Alpha, however you want to do it, that will show you the right shape. So on the lowest energy level, this H0 is equal to 1. So we can also ignore it if we only want to look at one lowest energy level. So now the wave function is a bit simpler. We can deal with this. We actually do some maths to this that isn't too arduous. So this parabolic potential simply looks like so. There is a maximum in the middle and it decays down to nothing. So that's telling us that the most likely position to find a particle is here, and it's increasingly less likely to find a particle any further away from the center. So let's check this with the maths. Let's see what the energies come out as. So we are going to ignore the constants and we're going to assume they all equals to 1. So Planck's constant 1, the frequency of the oscillator and the force constant 1, the mass 1. This is not an entirely insane idea. Our physicists like to use it because it's known as natural units, and what it effectively allows us to do is to get away with remove on all the gubbins that we don't need to worry about and just see a simplified version of it. We can really pick out the underlying physics by using natural units and making this assumption. So when we plug all of that into the Schrödinger equation, we end up with this. We've simplified the kinetic energy operator, we've simplified the potential energy operator. You might notice at this point, this is half times something squared. That's squared. And this is half times something squared. Put a pin in that, we come back to it next term. There is a simpler way of doing this, but it requires a bit more of a build-up first. Now if we put in the simplified exponential function, okay, this looks like something we could probably handle. So all natural units, this is going to remove our ability to get real numbers out of it, but it should show the underlying physics. So if we insert that, we get this solution. And what I want to focus on is ignoring that for now and just focus on that derivative. So if we want to take a derivative of an exponential function, we get the same thing back. We should know that it's going to be an eigenfunction. But the derivative of an exponential function is also multiplied by the first derivative of whatever's inside there. Well, that's known as the chain rule. So the first derivative of x squared goes to 2x. We're going to divide by 2, so that's going to cancel. So we end up multiplying it by x. Now when we take this next derivative of this, things are a little bit more complicated because we've got one function multiplied by another. And that requires the product rule. I'm not going to go through that in detail here. I'll just skip to the answer. We end up with x squared minus 1 here. So things are looking a bit more complicated now. We've got that tricky variable here, x squared. We want to be able to get rid of that, so we're stuck with the original wave function again. So let's put it back into where we started. Here's our x squared. Rather helpfully, there's an x squared there as well. So there are two x squareds. Maybe they'll cancel out. And if they cancel out, we've got ourselves an eigenfunction. And they do. We rearrange that, we multiply out the halves, and we have an x squared minus an x squared. Those are going to cancel, and we're left with a half overall. So if we apply the Schrödinger equation and the Hamiltonian operator to that function, we get an eigenvalue of a half. So the energy of that system is a half. That is the lowest energy on the harmonic oscillator is 1/2. And if you do it with the constants in place, it's actually a half times the reduced Planck's constant multiplied by the frequency of the oscillator. And that is the 0 point energy we came across in physical spectroscopy. It is the lowest energy you can get. It means no matter how low your energy is, how much energy you extract out of this vibrating potential energy vibrating thing, you're always going to get a little bit of energy left. So let's recap the harmonic oscillator. If we add in a parabolic potential, that is the half x squared or kx squared, suddenly we have to change the wave function. We're not dealing with sine waves anymore. We're dealing with this exponential. Of course, you should also remember that sine and cosine can be expressed as exponential, so this change shouldn't be too much of a shock. And the lowest energy we get out of it is half h omega, the frequency times Planck's constant. That gives us the lowest energy you can get. You can't extract that 0 point energy. And it means if we stick a particle in a potential well, it's always moving. We can't pin it down to nothing. That will come back to us again when we discuss the uncertainty principle and so on. But that brings us to the end of this particle model. We'll continue with a few more ramifications of quantum mechanics next.